announcement in case you have missed them. The second quiz is graded, you probably have seen that. I shared a little bit in this announcement how I plan to add those bonus points. So basically each bonus question is worth 1.25% of the total score, your score in this course. Unfortunately, I cannot figure out how to add these bonus points right now without messing everything up, so you probably see me. It's quite embarrassing to publish and then see what happens, and I know you are getting these announcements, but anyway, I need to figure out how to do this in Canvas. If you are interested in what your grade would look like right now, and just talk to me and I can kind of give you an Excel, which is how I end up doing things at the end of the course. I don't trust Canvas, so I have a big spreadsheet and calculate everything there. And so if you have any questions about that, just reach out to me. If you have amazing points, don't worry because you are good. Okay, besides that, I did finally also rate the project components, and you can see those basically here. You see the points, and all of these points sum to 100. So, if this is 30, that means that the 30% of the project is going to go to the final poster. I also wrote just a little description for each one of these, so I recommend you also check this out. For example, here I intentionally clicked on the final poster because it is going to be the most important deliverable for your project. And you can, if you read this, you can see I'm saying I'm going to also look at the content and how well the poster is, because we are going to have this poster draft component. This part, the final one, will mostly be focused on the content and experiments and all of that. So you can think about final poster version more as a final project report. And this is also a good mental, note of the date until which you have time for producing results, right? Once you put these results onto your poster, we are going to print them, and poster session will happen later, and you can bring, maybe a handout or something like, oh, I run an additional experiment or whatever for your poster, but 95% of your project results should be done on this day. So I won't go here, and click at each one of these, but I do want to warn you that because I didn't, give you really clear instructions for project proposals, and I'm also kind of late with giving you feedback, for project proposals, my grading is basically, have you integrated my comments or not? And if you have done that and you have produced a kind of polished version of your proposal, you basically get the points, and otherwise there will be deduction. So I expect, honestly, all of you will have points for the proposal, but don't take this as a sign that I'm going to be very relaxed grading moving forward. I'd rather I will, give you clearer instructions of what we are looking for. And for your next component, which is the immediate project report, the plan here for us, for how we are going to go about grading this, is to see what did you set as the success metric for your proposal for intermediate report, and we are going to see how far did you come to that metric. We, of course, if you have done exactly what you have set out to do, that would be like 100%. And then deduction, it's really hard to, formalize it because it depends basically on what kind of bugs did you encounter, if they are major or not. And, take into account that we have done so many research projects, we have a good sense of what kind of bugs are, oh, you have encountered this just recently and you didn't have time to fix it, versus, oh, this is something that you have probably needed more time to, fix. Also, if you have major bugs or major roadblocks, come up to me and Fatima, right? That's the most valuable resource that you have to kind of unstuck you and, also for us to have a sense of what's going on. Are there any questions? Yeah.
So do you want us to make changes directly in the original proposal
on the original doc, yeah. And I I know I didn't grade work, for example, so today finally I have a whole afternoon and evening just for this grading. So everyone can expect to get my comments in the Google Doc and then just integrate it into the doc. That's the easiest, and then I can just read the doc. You don't need to resubmit the grade scope. Yeah.
Okay. And would you want us to? Is there like a deadline for when we should have it updated by?
I will leave a comment about that in your doc, but you will have enough time. Yeah, don't worry about it. Any questions? Fatima also has made a huge progress on her automated circuit discovery. So if you need circuits, and I see some of you are like, yeah, then reach out to her. She will give you the latest version of her code. Also, talking about Fatima reminds me that Fatima is not here. Andrea, he's a PhD student at NLP group, has kindly stepped in for the camera work. Thank you so much. Okay, so I think that's it. Yeah, if I'm forgetting something, just let me know and I can cover it. But if there are no questions, we're going to continue with where we left things off, which is basically we were talking about activation patching. Does anyone remember what is activation patching and feels confident to give a little overview? Yeah?
Kind of. I don't know if it's confident, but I believe it was when you had a correct prompt, and a wrong prompt, you send in the correct prompt and record the activations or the resolutions. I can't remember which one was, but you record something, and then you pass in the wrong prompt, freeze it, and then use the correct prompts, activations in there, and then pass it through and see what changed, and you can record and see like what actually occurred.
Yeah, and can you tell me what kind of expectation in this setup you have? What kind of change would you like to see? So you have corrupt run and you have integrated clean representation. What do you expect to happen if this representation was causally relevant for the behavior?
Maybe I'm swapping it, but I believe you would expect it to flip to the correct answer.
Yeah. Yeah, because we have corrupt run in the first place, so we don't have the desirable behavior, and now we can introduce a clean representation, and we expect it to recover the clean behavior, which is the correct answer. So yeah, this is one version of activation patching, maybe even more common one than the other, which we call denoising, right? Because we corrupt run, you can think about it as a noise, and by adding the clean representation, you are denoising. So let me just write this down. Activation patching, denoising. We had clean run, which is, it can be with a fully clean prompt, clean embeddings. We have corrupt run with either corrupt prompt or corrupt embeddings, right? So we can change one or the other. So, for example, when I say corrupt embedding, what I mean, remember that example of the Space Needle is in downtown. Then we didn't change the actual words, but we did add noise to the embeddings, and this is how we corrected it. Corrupting prompt, we mean we actually changed the words. So instead of choosing Space Needle as a landmark, we would choose another one, right? And then we have corrupt run plus patch, where we take certain representation and output of certain components, certain MLP or attention head, and we replace representation that's coming out of that component with the representation, associated representation in the clean run. So for example, if I have chosen layer 3, and in that layer 3, whatever is the component, I have certain representation, I swap it with the clean runs representation in that location. Now, sorry, Samir, is it?
Yeah.
Samir, you We said also we could maybe swap the residual stream, and remember residual stream is the stack of representation over a certain token, and actually that's something that people want to do in some certain cases. So there you would take the entirety of that stack and swap it with the clean run, but leaving the representations of other tokens and their residual strings correct. So that's completely viable, although I didn't mention it last time. Okay, so now we have patched it, and remember corrupt run, the probability of the correct answer is it low or is it high? Low, right, because we corrupted it. So this is going to be low, and when I have this version of my forward pass, and if I will say patch representation, let's call it R. If R is causally important, what would happen with this probability? Be higher, yeah, I see one. Higher. And we want it to be significantly higher. Okay, so that was our activation patching, and then if you remember we had, we did cool things with it, with, for example, if we have these problems of a kind where we have the landmark and we need to predict the location of the landmark, we have found, parts of a transformer where that, factual associations are stored. We have also seen that we can investigate, okay, I don't have it here, but here it is. We could also investigate which components in a transformer are responsible for doing simple arithmetic with the 4 basic operations like plus, minus, and so on. Okay, so now, for today, I actually want to go into details of this paper that I talked a little bit about last time. And this paper is going to use activation patching, linear probing, describing the activations and things like that. Everything we have actually learned in this course, and it's going to be a really nice way to kind of wrap the knowledge we have about these methods. I think it's a great paper to read now that you have spent a couple of weeks with me here learning about these things. However, before we go into the details of all of that, I want to talk about another method that usually is associated with activation patching that won't be directly used in this work, but I think it's better that we cover it at the beginning of today's lesson and then go over this paper. So, the method I'm going to cover is going to fix or try to address one problem with activation patching. If I say that activation patching is resource intensive, could anyone tell immediately that you feel like you can explain what is a computational intensive here? Emma?
Yeah, well, I would imagine like in an LLM you have like a ton of different modules, a ton of different lanes. If you're going and patching each one individually and then seeing what happens, that might be expensive.
Exactly. So we have lots of components, and we need to repeat this for every single component, right? And when you say, Emma, computationally expensive, can you say that a little bit more concretely? Like what are we using the computation for?
Well, because we need to, in order to see the effect, we need to like get the lodges of the correct token. And so you have to like pass it through the entire LLM. And you're doing it, I think, are we doing it for each token too?
Yeah.
And for each like layer, or for each
Yeah.
MLP, each token.
Exactly. So when you say passing through the model, that's basically a forward pass. So I will welcome you all to think about how many forward passes we need to do activation patching, and for that we are going to use Gemma 3.7 billion. It's one of the newer open weight models. It's a third version of the family of models called Gemma. It's really good for following the instructions. It's post-trained and all the things you would expect from today's LLMs. The size is 27 billion. It's not small by no means, right? But it's something you can easily use on CHPC Python, for example. So it's available for academics, right? And you will see it commonly used. So now a little bit of digging in Hugging Face, I have found that Gemma has 62 layers. It has, or every layer that's attention layer is going to have 32 heads. And let's say we have only 5 tokens. So these, I didn't want to go crazy here because these, for example, for studying the factual recall, we have seen that we have things like the Space Needle is in downtown. So, okay, here we have 7 tokens, but, let's say that I'm really modest here and I have only 5 tokens. Then my basic complexity of my activation patching is, okay, I don't have this information actually. This includes layers that are both attention layers and multi-head attention layers. Sorry, attention and MLP layers. I had said attention twice. So I don't know how many of them are exactly attention layers, but let's say that half of them are attention layers. So I have 32 times number of heads, which is 32 plus 31. This is for multi-head attention over all of the layers. This is MLP. Then I have also all of this multiplied by number of tokens, right? This is basically the number of forward passes I need to make to produce a heat map like that, right? And because I messed up in my notes, I don't know exactly what this value is. Let me quickly use a calculator. So we have 31 times 32 plus 31 times 5. That will be roughly 5K forward passes. And to make it now very dramatic, this is for a single instance, right? So if my data set has 100 instances, which is a common and the smallest, number of instances for analysis, this is going to go from, we are going to have 500, like 500,000 of forward passes, right, to produce an analysis of this kind, right? And it's a lot of forward passes, right? And again, it's not like you cannot do it, right? These papers do exist and they're actually produced on academic compute. Rather, this is really slow, right? And to get your insights, you will spend a lot of time. So this motivates new method, which tries to overcome this computational intensity of activation patching, and this method is called attribution patching. Attribution patching is basically starting with the observation that when we are doing activation patching, we are checking the difference between the outcome, right? So here we said the probability of the correct answer had increased when we had denoise with the clean representation, right? And if you remember last time, did I actually write the logics? I did, right? We said that our metric cost of choice will be the logics of the correct answer, right? And then we said we are going to check what is the difference in the logics of the correct answer when we use we have a corrupt, right, activation, and we replace it with a clean one, versus when we just have corrupt, right? This brings up, did I actually write this last time? Okay.
Something along those lines, yeah.
Okay, cool. So just to repeat, with this equation, basically what I've done, here I said, okay, we are comparing whether the correct answer is now more likely when we have done denoising, and I've just written this down. The only difference is here I'm using logits instead of probability, and that stems from, now you know all too well that we would rather stay with something that's linear with respect to other components. Okay, so attribution patching starts with observation that we are basically trying to measure by how much L changes when we move the activation, A clean, from component C. So C is a component like MLP module or attention head, to the patch, or sorry guys, we were talking about denoising case, and my notes are about the denoising. So when we move the corrupt one to a clean one. And we can also ask if we move the clean one to corrupt one, because we have these two versions. Right. Well, just write down so you remember that when we move from corrupt to the clean one, this was what we call denoising, and this is what we call noising. Just make sure I'm on, I need to choose denoising or denoising, because I want to see what I have in my notes. Okay, so I have in my notes noising version. So I'm going to try to, on the fly, write the denoising version, and hopefully that I don't mess anything up. I'm just going to delete this for a moment. Okay, so now we're trying to approximate how to measure this change without actually fully doing all these forward passes. So that's our goal. Basically, calculate this change, approximate this change without running all of these forward passes. So goal, approximate, I will note this as a star without running this many forward passes. And the way to do that will be based on the Taylor expansion. So, just to remind you, first order Taylor expansion of some function, scalar function that's around the base point v0 is going to be given with this equation. difference between a function f, which is a scalar function around v0, when we move just a little bit and get to v, can be approximated by taking their difference vector and projecting it onto the gradient. Let me show you a little visualization just to remind you of this. So let's say here, this one is a good one. The other one will become problematic. So if we have the difference between our activations being this much, then my projection of this difference onto the slope, which is given by, here we are working in a 2D space, so we just have the tangent, right? There we are just writing a gradient to approximate for when the input space of V is high dimensional. But when we project our difference of these two activations onto the tangent, we are going to come somewhere here, right? And the true value of function L for one of these activations is this green block. And you can see they are very close to each other, and the difference between the value of the function L is approximately the same. Yeah.
Is it like it says here where we're doing it based off of the gradients of V0 versus the function according to V, or does it matter which gradient we're projecting this vector difference into?
I didn't quite hear which alternative you are talking about, but it is important which gradient we are taking. So we're taking the gradient of function f, and we are going to next map it into the terminology of L and our patching and all of that. But we are taking the gradient of the function f with respect to v's, the inputs of the f, and then we take that value in v0.
Okay.
Yeah. Okay, so this is just a reminder of general equation for first order Taylor expansion, and then here I'm just visualizing what we are doing there. The thing to remember is you basically take the difference and you project that vector onto the tangent of the function in a given point, this starting point here. Okay, so now let's map that with our terminology with else and patching and all of that. So our function, so now we come to what is actually attribution patching method, is basically then introducing L as our function that we are using the first order Taylor expansion. And I will also say that, okay, doesn't matter. So now we are going to add L here. So our F is going to become L, which are the logits of the correct answer. And now this is where I need to be careful because we have these two cases. So I'm going to write as it is in my notes just to not make the rest of the lecture messy, and then we are going to talk about which kind of patching this is, noisy or denoisy. So okay, if I start with a clean run and I move into the corrupt activation, what kind of version of patching is this? Noising or denoising? Noising, right. So this is a noising version. And if I would like to derive attribution patching for denoising version, I would just start with the corrupt and move into the clean. Everything else stays the same. Okay. And the gradient with respect to what is association. Okay, so now notice that this is basically the difference in function f, right? So this is delta f. And here I have delta L, right? So I start with delta L, and this is going to be approximately then, and now I'm just using this equation, but I'm using my function L instead of F, and I'm picking the activations for my vectors. So I have V minus V0. What is V? It's incorrect activation, right? So it's going to be corrupt for this component minus the clean. And then I have the gradient of L in my with respect to V, which is this corrupt version, right? Okay, just check. Okay, this is going to be, I'm going to write A here, just to make it clear for you. So I have all of these possibilities for what the activation can be. So imagine L is something like 5A, right? Plus some other variable X. So when we say we are calculating gradient of L with respect to A, it means we are taking care of these possible activations here. Like we think about more abstract formula, and then we take the particular value of that gradient. So, for example, let's say this was 5A squared, the gradient of A with respect to L would be 10A, right? And now the gradient of AL in A equals 1 would be 10, right? So just to make sure that you understand the notation of, we are taking the gradient with respect to, but then we take the particular value, right, for A. So here we take the gradient with respect to A, but we are going to take the actual value in V0, which is for us a clean of C. Okay, this is it. This is basically what attribution patching is. So we have this formula, and now we approximated that value with this formula. And now it's really important that we recognize why did this help us, right? Why did this change the number of runs? Well, here we can make a forward pass, right, to collect the corrupt activation. So I have a corrupt run, and with one single forward pass with the corrupt input, be it with tokens or embeddings, I can collect a corrupt C for every C, right? In the single forward pass, right? Then to get these bodies, we just make our clean run, right? And with a single clean run, I can get all of these activations from the clean run, so for every C. Great, so 2 forward passes to collect all of these. And now I need also this gradient, and that requires 1 backward pass, right? So backward pass for all gradient of A, A clean C. So my problem of needing almost 500,000 of forward passes when I have 100 instances and 5 tokens and a model of a size 27 billion turns out into a problem where I need just 2 forward passes and 1 backward pass. So obviously we achieve. I feel like there is a natural question when you see that we have simplified the problem this much. Without saying what this natural question is, does anything immediately comes to your mind?
Well, what comes to my mind is, why even bother with activation patching if we have this simpler solution that does it in 3 instead of 500,000?
Exactly, right? So, you know, if we have something this cheap, why would we ever use activation patching? Or in other words, we embrace the fact that this is an approximation, right? First order Taylor expansion of the function L, the function that quantifies the logic of the correct answer. And the question is, when does this approximation hold? And when does it work, right? And the answer is that it doesn't hold always, and it does break. But there are also situations where it works. When it breaks, when it works, there is a lot written on that. I will just return to my visualization and discuss one case, which is the most natural one. So, so now the question is, when is attribution patching a good approximation, right? And one obvious case where attribution patching is not a good approximation is where Taylor expansion is a good approximation. And that's basically, I'm going to now return to this visualization, is where we take such a big displacement, let's call this displacement, the difference between two vectors. So we have moved from our starting point V0 so much that we are not anymore where the original function, L or F, is linear, right? So if you stay here around this point, and then your function is behaving almost like a slope, just a normal line. However, when you take a big displacement and you move all the way to here, now this is where your function is actually curving along this distance, right? So here, in this distance, it's almost like a line, right? Over this distance, now we have this bend. And when you have this bend, this linear projection onto the tangent, onto this slope, will not work anymore, right? And here is where we are going to get bad approximations. So just to visualize, so here we have the displacement. This is our V0, and this is the gradient or a tangent in the point V0, right? We are doing the projection of this vector onto this blue line, which is the tangent, and we get to this point, right? And this is our approximation of the function f or L in this point activation here, right? However, what is the real value of function f or L is this green point. So now my difference of the function L or f is this much, where in reality is actually this much, and I have that approximation. So basically, when you take a big displacement, I'll write V minus V0 because it's easier than these activations with all the subscripts, superscripts. So a big displacement with minus V0 will basically bring us into a regime where our function f is actually curving along that distance. So function f is curving along that distance. And we break the linearity assumption. That Taylor expansion makes. Right, so Taylor expansion says, well, if you move just a little bit from V0, your function is behaving basically like a linear function, and then you can do something like this. So when are we making big displacements, right? When are we making these huge differences between activation? And this comes to the point that Samir, you mentioned about taking the entirety of the residual stream. So if I, instead of patching just one activation, one representation at a time, if I take the entire stack of representations for a given token, then the difference between the stack versus stack is going to become, or it has been shown that it's large in magnitude, and that's going to then cause all this trouble. So it can happen. I mean, we are patching patching large components. This is just one example, like entire residual string of a given token. Okay. So this is one place where you need to be cautious. And then I do not want to go over all of these because let me just open the attribution patching. So there are many other cases where this attribution patching can be bad approximation. It has something to do with, again, layer norm, right? Who would say that layer norm is this most important key of the trust ladder? It has something to do with how deep we are doing this backprop, and earlier layers may have worse approximations than the later layers. Non-linearities can saturate, and that can cause issues. There are many, many cases. So I'll just say plus many more without spending more time on all of these cases. But that leaves you with a practical question of all right, Anna, you just told us this method, but it seems like we don't know when to use it. So when can we actually use it? Because this situation is really appealing, right? So one practical advice I would give you is that you take a sample of these activations that you are trying to check the causal effect on, and you calculate their attribution, and you can get a range of them from being very low attribution, meaning like they are not important, to mid to really high, right? So you get, let's say, 10 activations with the, in each one of these categories, and you have about 30 of them. And then for those, and only those, you do activation patching, right? And then you can check whether you have correlation between your attribution and activation patching. And if you do across these values, that kind of suggests that in your situation, this might be a reasonable method to apply on a large scale. So I will say practical advice is kind of do a sanity or soundness check of attribution patching on a small sample of data. So soundness check of attribution patching. So that would involve first, number one, run attribution patching. And then let me see how to say this, order component C by delta L, right, that you get from attribution patching. And then you can have 3 bins. You can have bins with low delta L, mid delta L, and high delta L. So that would mean this component is important, somewhat important, really not that important, according to attribution patching. I'll write it down. So low difference, it means not important. C, not important. C, somewhat important. And C is important. That's what attribution patching is suggesting. And then you sample, maybe 10 from each. Okay, so now third step is for every C in, let's call it C filter. So here you have chosen C, you have 30 of them. You can actually do not attribution patching, but activation patching. and you get values of delta L for that component with activation patching. So here we have delta LC of attribution patching, and your final step is correlation between these values. Between delta LC attribution patching and delta LC activation patching. And if it's high, then you use attribution patching on for your analysis. You're kind of confident that whatever insights you're getting from attribution patching probably makes sense. Okay, so that's basically it, what I wanted to say about attribution patching. Just to kind of overview everything, we have talked about activation patching, which is a method that tells us which component, meaning which MLP or attention head, influences the behavior of the model for a particular data. And we have used an example of factual recall where we had inputs being landmarks and we need to predict the location of the landmark. And activation patching is nice, like conceptually, but it has a practical problem of needing too many forward passes. And today we started with the motivation of trying to make another method that is behaving like activation patching, but is much more computationally cheap. And we start with the observation that at the core with activation patching, we are trying to measure the difference in the logic of the correct answer by doing the patching steps. And we then decided, well, we know from our math background that Taylor expansion might come handy here. Basically, the first order Taylor expansion gives that the difference of a function f between a point v0 and a point v that is removed just slightly from v0 can be approximated by linear projection of a vector of the difference of these two vectors onto the gradient of the function f in the first point. So that's just our math background. We are like, okay, cool, this already approximates the difference, and we do need the difference, right? So we take it as our approximation of the choice. So basically what we have done is plug as a v and v0 our activations of a given component, either clean or corrupt, and this gradient is gradient of the logit of the correct answer in the starting point, which again can be corrupt or clean depending whether we do noising or denoising. Here we have done noising version, so this is the equation we come with, and that's basically it. As previously we got the difference of the logit by doing the full activation patching. Here we get it in a much simpler way, and we need only 2 forward passes and 1 backward pass. However, obviously now we have simplified things, and the natural question is this approximation good or not? And then we said, well, not always, definitely not always. There are many cases where this approximation might break. I have just highlighted one case where we make a big, we move too much from the starting point, and our displacement is large in magnitude. And because it's large in magnitude, we basically can have a situation where our function curves over that distance, and first order Taylor expansion, which assumes linearity of the function around small distance around v0, no longer holds, and we will have that approximation. And I said that one case where this can happen is when we are trying to patch too many components simultaneously, such as taking the whole residual stream of a token, right? Like we maybe want to say, what's the influence of these tokens, of this particular token of the entirety of this behavior? And ablating, patching its residual stream is a natural experiment to do, but can cause trouble. So there is many more, I said, and my practical advice is, well, try to use it. You run it, and and then do a little soundness check where you check the correlation between attribution patch and activation patching for same data on a small sample. And if the correlation is sufficiently high, that gives you a hint that maybe attribution patching is okay. Yeah, Zach.
So are the differences usually too large to go to a higher order and we still aren't getting a good approximation, or is it just that the function becomes too nonlinear within like that space?
So yeah, so this particular case where we take a big displacement can be kind of connected to the function becomes nonlinear, truly nonlinear, because it is nonlinear going along that distance. But you did mention the higher order interactions, right? And maybe you would like to take second order, Taylor expansion. And this is what Neil Nanda is here discussing under multi-feature dependence, right? So here, when you do first order Taylor expansion, you are not assuming any interaction between features, and you are canceling those second order derivatives which would measure that, right? So you are simply ignoring them altogether, and there are cases where that's not a good idea. So he goes into more depth with that. So when I say many more, there is really, it's a really long article, yeah.
Sweet.
Yeah. So I think it's hard to try to have a nice mental model of all these possibilities and test specifically for them. I think practically it's better to just check the correlation with the activation patching. Yeah, because many things could go wrong.
Yeah, it feels like you're kind of just reaching back to the original activation patching as you like try to test higher order. Like you just keep like adding higher
exactly.
orders.
Yeah, that's right. Okay, any questions about activation or attribution patching?
If you're doing this systematically with a set of prompts that you care about, is there a reason to think that this might help you spot sort of problems in how the knowledge is represented?
Yeah, there is one recommendation that for example, these two activations can change a lot if your corruption prompt is too different from your original prompt, right? Like if they are semantically very different, their representations are also going to be different, and then you are yet again going to have this problem where the magnitude of this displacement vector is big, right? So the recommendation is also to not try to, if you're doing the corruption of the token of the prompt rather than embeddings, although with corrupting embeddings as well, due to the fact that you are corrupting, you can have these large, differences. So trying to have these crafting the prompts and clean and corrupt RAM in a way that won't immediately cause this to be too large is definitely a recommendation. And being careful about changing as little as possible, but being able to corrupt the behavior is definitely something to try when you're doing this. Yeah. So,
I guess I think you're essentially saying this, but just make sure. But I mean, if we swap out tokens, that's a large displacement. That's likely to happen. But if we're just adding Gaussian noise to our embeddings instead, we can control that parameter. And it'll likely, we could only add a very small amount in our activations. Probably.
Yeah, and I think this is why, for example, Factual Recall have used the noise version of corrupting, and they have, they say we are going to set the value of noising to be 3 times larger than something. Like there is definitely a balance, they consider where you're starting with, so you're definitely on the right track here. Question?
I guess I'm just adding Gaussian noise to activations just doesn't seem like, it doesn't seem like as useful.
As interpretable.
Yeah.
At least, yeah.
Sorry, Seth.
You set a little bit harder in the way together and you disagree. For sure it's less interpretable in a sense that if you have created a correct prompt and corrupt prompt and you can tell it's just this semantic difference between them. if you have added a little bit of noise to embedding and you lost the behavior and you can recover it on a certain token's position and its representation. Because remember, I did talk here about component, but every component is also, relative to the position as well. So I don't know, I think you kind of recover, if you can recover at this particular token, particular layer, the behavior, that kind of suggests, oh, corrupting this particular token and the noise in it, cannot recover behavior. So I still feel like you get kind of the similar thing, yeah. Zach?
I just have one more thought that has crossed my mind while we've been talking about this, but it feels like we can almost measure confidence in our embeddings in some way with this. Like, I haven't really thought about this at all, and I don't know if it really makes sense or not. But adding some sort of noise to it, it feels like, I don't know, the more displacement or the more noise that we add, right?
That's an interesting thought, but I would say for me that would measure the sensitivity right? If you add a little bit of noise to that token's embedding and it just changes the behavior just drastically, it does is that the model is sensitive to that token's representation, which can be either good or bad. You can say, oh, that token is important, or you can say, well, the model is robust because I can adversarially attack it by just adding a little bit of noise. But I didn't make a connection with confidence before. Is your idea, okay, if I add noise and it shouldn't make any difference on the behavior, but it does, you kind of suspect that the model is a little bit not confident, and you can trace it to that embedding?
Potentially, that's kind of like where my mind went initially with this idea is like, okay, if we add, we can add varying levels of noise, and after some point, we're gonna disturb it so much that our logics change sufficiently.
Yeah.
And now
Maybe. I mean, it's a really interesting coincidence that you mentioned that because I shared this morning a paper on Professor Slack is not a good thing to open in the midst of teaching. We are gonna open papers. If I ever find, there are just so many of these. Okay. All right. So why I'm bringing this is, you're bringing this interesting. We are kind of discussing this interesting connection between sensitivity and certainty and importance and all of that. And just this morning, I have encountered this position paper which says that all of these model failures, and they say from hallucination to homogenization, are different facets of miscalibration. Miscalibration refers to models giving wrong predictions, but very confidently, right? When you would expect more uniform probability distribution where the model is not confident. And they have this nice little visual here on this, kind of 4 different types of problems, and they're trying to make an argument that it all comes down to the miscalibrated confidence and certainty measures. So yeah, maybe we need to rate this and see if it maybe helps this discussion. Yeah. Okay. Any questions?
What paper was that?
That paper, I can share it in Canvas, but it's this one. Position, large language model failures from hallucination to homogenization are different facets of miscalibration. Homogenization refers to the fact that most of our language models today give basically kind of the same responses, and that's not really what we want because they are currently assisting us with code writing, with general writing, with a lot of things where creativity is important, right? And if every single LLMs is telling every single person on this planet do the same thing, we are losing this diversity that's really important in this society. Okay, so if there are no questions, I will just go over this paper to wrap Would we appreciate like a 2-minute break maybe to reset before we go into this? Not a bad idea. Okay, all right, let's take 2 minutes and then we'll go further.
It's also like, I don't know, when okay, I found that you can like replicate by changing or like, is that really like anything else? Yeah. I don't know. Does that make sense?
Yeah.
You want us to?
Like, I didn't fully explain it, like, if you're just adding noise to the activations, then it's like, okay, we found how we can like break it by adding noise. I'm sure it scrambles my neurons in my brain and sort of saying, yeah, this makes sense also.
Yeah, yeah.
So this is on, and the correct answer is CBS, and this represents transform. So every pink circle is either MLP or attention head, and every red, I think that's it. Yeah, sorry, no. Every circle is a representation of that token, right? It can come from attention or MLP. So what we do with patching is we take, let me just check, this is the denoising version of patching. We first add a little bit of noise to important entity in this input, and then we make a pass again. And now our circles are corrupt. See, these circles, they are associated with the run that is corrupted. And we just take one of these at a time and swap them with the corresponding clean representation. And if that's swapped, we can go from not CBS into CBS. We say, well, that representation is sufficient to recover the correct behavior. And then we can, start from the corrupt, from the clean run and add the corrupt representation, and then break it, and then say it's necessary to. So that's what we are doing, right? And this, when we say, okay, the different elements, the difference we get at predicting CBS when we have exactly. Ability to answer, and then see whether we can recover, right? So that's what we are doing. But it requires this patching and checking the, what is the outcome for every single one. And this basically just
It's just using like all the calculations.
Okay, let's get going because we have only 15 minutes and I really want to finish this paper so we don't keep coming back to it. Let me do this something. Oh, it's okay. So first, we are going to talk about this paper, Arithmetic Without Algorithms. And remember the last time we have seen that this paper shows that at the population level, LLMs are solving simple arithmetic tasks with basic operations by using different heuristics instead of using robust algorithms or purely memorizing. And in this work, they use a bunch of these methods we have seen after sparse feature circuits. So it's a nice way for us to see how these methods can be used to do fun research and get the IPO publication out of it. I don't know whether that's the best end goal, but it's a nice kind of like a recap of the methods we have read so far. And also something that I didn't emphasize last time, you can basically build a circuit from these methods, right? Although we have seen a completely other way of building circuits, which is sparse feature circuits. So today we are going to go through the method, talk about what their circuit is and how these two methods for circuit tracing and discovery differ and what are benefits of one or the other. So just as a reminder, we have talked about circuit tracing before, and we have used this definition by Ola et al. From Anthropic that circuit is a subgraph of a neural network where nodes are featured directions, and the edges between two nodes are basically the weights, kind of like impact of one feature onto the other. And I also said that this definition has been relaxed over time, and you will see circuit discovery works where nodes aren't featured directions, but rather they are just a full component, like a full MLP or full attention head. And the connections between two won't be these weighted edges, rather you will say, okay, this component is important, and this one is, and this one comes before it, so we'll just connect it or something along those lines. Okay, now the setup in this paper is they are going to evaluate LLMs on 2 operand arithmetic prompts with Arabic numerals and 4 basic arithmetic operations, such as minus, plus, divide, multiply. And all of the prompts are going to be of this very simple form. And they use LLMs that are going to produce 4 prompts from each one of these prompts. 1 prompt for the first operand, one token for the first operand, 1 token for the operation, 1 token for the second operand, and 1 token for the equal sign. They're going to take 100 examples for circuit discovery and 100 for testing. And all of the examples are going to be properly answered by the model, and the goal is to understand what does the model do when it correctly answers these kinds of prompts. And the focus of the paper is in Llama 3.8 Medium, and they have other elements in the appendix. So first question, they have this sequence of questions, and the sequence of questions is basically building their hypothesis of what the model might be doing for these kinds of prompts, and all of them together leads them to discovering a behavioral circuit, right? This stands in opposition to the kind of sparse feature circuits we have seen, where you start with a replacement model, you do an attribution graph and all of that, where you go more from a bottom-up approach. So, the first question they ask is which layers affect the arithmetic outputs. And it would be great if I haven't shown you this, because then I could, for example, imagine you have this on your quiz, like I ask you, which kind of method you can use here. Now we have just talked about activation patching. You can be like, yeah, activation patching is a great method to inspect which attention head, which MLP is responsible for giving me correct answer for arithmetic prompt. So they basically use for clean run their normal prompt. For corrupted prompt, they use the fully different prompt, which it comes into that potential problem of what if the change is too large and now your attribution patching wouldn't work. But it doesn't matter because they're using activation patching, right? And then they, replace activation from corrupt run with the clean activations, and then they see how they can recover the behavior. So if the patching restores performance, which is indicated by this value, the difference of logic for the correct answer, the higher and more intense this value in color are, then the more responsible that component on that token position is for recovering the behavior. And what we see here, we said last time, is most of the attention heads don't play a big role here. It's mostly MLPs at the very high levels or at the mid layers. Now, so the main conclusion out of this experiment, mid to late MLP layers play important roles for predicting the correct answer for these arithmetic prompts. I will make a note that they use a slightly different L function here. So our function L was just the logit, the logit of the correct answer, and we were checking what's the difference of the logit after denoising, right? Here they're using, let me write this down. So P and R refer to prompt and result. So prompt P, result R. When you make a corrupt prompt, you denote it as P prime, and here as R prime is its result. So what they're using as their function to measure the logit change is this equation that takes two things into account: whether the probability of this wrong R prime answer decreases with denoising. And whether the probability of the correct answer is increasing with the denoising. So this is just I'm making a point out of this because I said, very often you will see as a choice of metric L to be the correct answer logit, but you can see different versions, right? So don't be confused if you see different function. Another additional thing we use is so-called circuit faithfulness. So now this assumes we already have a circuit, right? Which might be surprising given how much work we have done to get to sparse feature circuit, and suddenly we have a circuit. The point here is that the circuit we get out of this is much simpler. So basically, what they call circuit here is, let's go back to this representation. You have layer 1, layer 2, all the way to how many we had in Gemma 62, right? Was it? Let's say we have 62.
Yes.
Yeah. And some of them are whatever, MLP and then attention or other way around, doesn't matter. And this, and we have positions, right? 1, 2, 3. Basically, from this MLP visualization, we know, well, this layer and this MLP is really important, maybe these ones here. So basically, you can think of the things that we choose to be important under some threshold. Let's say we set the threshold to be 4 here, and then see which components survive. This makes our circuit here. This is what the circuit refers to. Basically, this subgraph, like this, right? This is a subgraph, computational subgraph of a regional transformer here. So basically, we have found some components to be important for each position, and we have kept only them under some threshold here, and this is what makes our circuit. So much, much simpler. And to test whether this circuit is faithful, what they do is measure the so-called faithfulness of this circuit, which is basically checking whether circuit alone behaves like the full model. So they define a function, they call it ML, which is the logit of the correct answer versus the max logit in the that you get in vector. So correct answer doesn't necessarily need to have be the most likely option, and they are normalizing with respect to the max logit. And they check as a faithfulness of our circuit C. They are checking. I will write something first. They imagine we just check this value. What is this value when we use only the circuit relative? What is this value when we use the full model? These two things should be kind of the same, right? So we would expect the perfect behavior here to would be something around 1. However, they are also checking doing this subtraction with respect to zeroing out everything or mean ablating. So ML nothing is very often the value of this function NL when all of the representations are set to mean value in some data. So you have some data and you check what is this, let's say this value, this representation across all of these. We check the mean of that value representation and we make a transformer version with all of these mean representation. The idea being this mean ablating your model is almost like what would your model do a priori, right? Like for this data, like what is the average thing your model would do? So relative to what your on average your model would do, you check the difference between these two values. So now if this is close to 1, this is great, your circuit is faithful, and in their work the circuit accounts for 96% of the entire model performance, so they get 0.96 here, and they say, okay, this is pretty good. Yeah.
What does M represent in this case?
M is a full model.
And then C is just the circuit?
Yeah. C is M without not C, right? So you just remove everything that's not in the circuit, and that's your circuit, right?
Okay.
Yeah, that's computational software. Okay, well, seems like I was very ambitious with what I was thinking we can do today for this paper, so we're going to stop here. We don't have more time, but basically next time we are going to cover everything they've done, and then finally kind of compare it to the approach of sparse feature circuits, which I think is important for you to kind of know why would you do that complicated approach when you can get some insights from this kind of approach. Okay, let's stop here.